All right, so we're ready now to finish up section one or chapter 1B. We will be looking at logarithmic functions here. And if time permits, we'll start to look at chapter 1C, where we'll be introducing trig functions. Now, trig functions, of course, are something you've seen before, but it might have been a while since you've seen them before, so we'll do a lot of reviewing because it'll be awfully important throughout the rest of this course and Calc 2 if you go ahead and take it. But right now, let's focus our attention on logarithmic functions. And this is one of those areas that is very heavily used in applied fields. Let's just quickly review what a log is. Let's just say, for example, we have the following statement, y equals 10 cubed, which of course is equal to 10,000. Now, if we take the logarithm, and if you notice there's a base here, base 10 of 1,000, that turns out to be equal to 3. Now, basically what's happening here is that when you're taking the log of a number like this, what you're looking for is the exponent, which when we take the base and raise it to that exponent, gives us back the original number. So in other words, here, by asking for the log to base 10 of 1,000, what you're really saying is what exponent of 10 equals 1,000. And of course, as you can see, that's equal to 3. Okay, so we can say that the log base 10 of 1,000 is 3 because 10 to the third power equals 1,000. Now, I do want to point out here that if you're using a calculator like the Texas Instruments TI-84, there are two actual log buttons on here. The one next to the 7, it says log, just plain log. It doesn't explicitly say so, but this button is log to base 10. The one below it, ln, stands for natural log, which we'll discuss in a minute. Now, you might wonder, why don't we have all the other logs here? In other words, why don't we have log base 2, log base 5, and all the rest? It turns out that it's not necessary. There's a formula that we'll be looking at in a while that enables us to calculate the log of any base from another log. So even the 10 log 10 and the natural log are redundant to a certain degree, but most calculators will have at least the natural log and the log to base 10, because those are the two you're most likely to run into in practice. All right, let's take a look at a few other simple examples. For example, the log base 10 of 1,000,000 is 6. And again, it's because 10 to the 6th power is 1,000,000. Now, here's a different one, log base 2. Log base 2 of 8 is 3 because 2 to the third power equals 8. So again, the way to think about this is when you take log base 2, you're asking what exponent of 2 gives us 8, and that in this case is a 3. And then similarly down here with log 3 of 81, this is equal to 4, and that's because 3 to the 4th power equals 81. So these two statements basically mean the same thing. In other words, one implies the other, and vice versa. Now, I just want to mention here, sometimes log base 10 is referred to as a common log, partially because we see it on a regular basis. Like, for example, the Richter scale, which you've probably heard of, which refers to the strength of an earthquake. You may have heard that going from one number to the next, for example, 6 to 7, means the earthquake has gained in intensity by a factor of 10. That's because the actual scale is in terms of powers of 10. So in other words, 6 really means 10 to the 6th power in the scale, and 7 similarly means 10 to the 7th. So clearly, going from 6 to 7 means that we're increasing the strength of the earthquake by a factor of 10. So it's not, in science, we often see these log scales being used because it's just more convenient for some reason. Another one that you've run into before in biology class in high school, you might recall the pH scale, which refers to whether or not a liquid is an acid or a base. For example, 7 is the pH of water, which is neutral. Anything below that is an acid, all the way down to 0. And then the higher numbers are for bases. So those actually are exponents as well. And so although it's easier to think about the actual numbers like 3, 4, 5, whatever. Those are actually exponents of 10. All right. Now, how about the natural log? Now, what's happening here is that you have a log with the base of e, which you may recall is a constant, which is approximately equal to 2.71828. And this one has its own, not only its own name, but it has its own spelling. We often see it abbreviated ln for natural log. And this is something we'll run into a lot in applied disciplines like, let's say, finance and economics. It's often used to help us understand, for example, if we start out with a given sum of money today, how much will we have in the future? That type of question can be answered often with the E. And so natural logs are based on base E, and we'll probably use that more often than any of the others. And again, as I mentioned before, on the Texas Instruments calculator, you've got the two buttons. I don't know if you can see that or not. Oh, it's backwards. Okay, well, the log is next to the 7, and natural log is next to the 4. Okay. Yes, I should have thought about that before I held it up to the camera. Of course, it's going to look backwards to you, but that's where they are. Okay. Now, by the way, the iPhone has this too. If you want to use your iPhone calculator, just a quick tip here. You know that it's one of those apps that's built into the phone. It comes with it. If you have the phone, you have this app. So when you click it on, you look at it and say, wait a minute, that's a very basic calculator. I don't need that. But if you turn it on its side, oh my God, look at all these functions it has. It is now suddenly a full-blown scientific calculator. And if you look very carefully, you'll see that just to the left of the 4, you'll find the ln, or natural log button key. And then to the right of that is log. And here they've explicitly labeled it log base 10, so that it's clear that that's the one you're looking at here. This one doesn't do that. It just says the word log. Okay, but either way, it's the same thing. All right, actually, this thing is surprisingly powerful. There's a lot of good stuff in here. I mean, if you really find yourself without your Texas Instruments calculator, a lot of what you need to do can be done right directly on your phone. And I know that you never go out anywhere without your phones. All right. So anyway, now obviously Symbolab can do all of this for us. All right. A couple more simple examples. The log base 3 of 9 is 2, because we know that if we take 3 and raise it to the second power, that'll give me 9. And this one, we've just seen it before, but log base 2 of 8 is 3. So just in the most general possible terms, log base b of x means the same thing as b to the y power is x. So just a quick reminder. This statement is equivalent to saying, okay, and that's because if this is y, this is b, and this is x. B to the y equals x, y equals log b of x. Now, I do want to point out here, though, that because of the way logs are defined, any log which is less than 1 is going to be negative. Okay. Now, that's because, let's say here we have the example log base 10 of 0.1. Remember that the log is some exponent of 0.1. So that means that x cannot be 1 or greater. In other words, if x was equal to 1, then we would have 10. So the fact that it's less than 1 indicates that the result will be negative. Now we can confirm this with Symbolab. I can show you a graph of any logs we need. Let's start, for example, with log base 10. If you can see what's going on here, the function crosses the horizontal axis at 1 comma 0. So in other words, the log of, let's say, log base 10 is 0 because, oh, I already had it right there. I didn't even see it. Okay, very good, even better. All right, so log 10 of 1 is 0 because 10 to the 0 is 1. This is going to be true for all logs, no matter what the base is. The base raised to the 0 power is 1. So any log that you have, it doesn't matter what the base is, it's going to cross the x-axis at this point 1 comma 0. Okay. After that, the function will rise continuously, but at a progressively decreasing rate. And below that, it becomes negative. Now, if you notice, it continues to shrink, but it never quite reaches the vertical axis. So this is an asymptote of the function. And the reason for that is because no matter how small this number is, you're never going to get a 0, okay? In other words, you cannot have a number where when you raise it to the 0 power, it's going to give you anything other than 1. So that's why this thing can never actually be 0. Now, as it turns out, the basic shape here is the same no matter what the base is. In fact, what I'm going to do is show you right now how this would look if it were, let's say, ln x. And you'll discover, whoops, I forgot to hit the go button. Yeah, I mean, if you can see the difference between this and the other one, then you have very good vision because it's very, very similar. Okay. It's going to have an asymptote on the vertical axis, which means that the function can never reach 0. Or I should say, is x can never be 0. And then y, on the other hand, can be any number. Okay. In other words, y can be anything from negative infinity up to positive infinity. It's the x that's restricted to being strictly positive. Okay. In other words, x cannot be 0. If you try to take the log of 0, it'll come back with an undefined or error message in the calculator. Okay, so just remember, just in general, remember what the base is. The log of anything less than 1, let's call it a. And then finally, the log base b of 0 is undefined. Okay, and that's true for all bases. Right. So this makes it possible then for us to define the domain and the range of any logarithmic function. Right, it doesn't matter. And by the way, I just want to point out that when you see this little b here, this means that this is true for any base. And also I want to point out that some books, when this is true, they simply write it like this. they just leave out the base altogether. When you see that there's no base, that simply means that whatever the statement is, it's true for all logs, regardless of the base. So the range of log x is the entire real number line. You can see that y can be anything from negative infinity. And this curve, although it's rising very slowly, will eventually reach positive infinity, or it goes up forever. Let's put it that way. It never actually starts to turn down. So the range of possible values for y is everything between positive and negative infinity. It's the x's that are restricted to positive values. In other words, it can't be 0, but it can be any positive numbers. So here we have the interval from 0 up to infinity, where 0 is not included. Okay, so x, the domain rather, is strictly positive. Now, we've already seen that the log to base 10 is known as a common log or common logarithm. And so we've seen a few examples. Let's look at another one here. Log base 10 of 10,000 is 4 because 10 to the 4th is 10,000. And of course, natural logs, as we've already discussed, are have a base of e. Now, I don't know who chose the name natural, but it's an appropriate name. I mean, the majority of the time when you're using logarithms, at least in, well, I shouldn't say that, but at least in financial related applications, almost without fail, if you're using logs, it's a natural log. For certain disciplines like maybe chemistry and physics, it might be the other way around. But you don't run into the others very often, like base log 2 and 4 and 8 and those others. And again, two key properties, no matter what the base is, the log of 1 is 0, and the log of, oh, and here's one we haven't discussed. The log of its own base is 1. Okay, so like here, for example, the log to base 10 of 10 is 1 because 10 to the first power is 10. So this will be true for any base. So that means, for example, the log to base 2 of 2 is, of course, equal to 1. Right up here, though, they're reminding us that the log of 1 is just 0. That's the where the function crosses over the horizontal axis. Now, here's where it gets a little bit more interesting. We're going to need these properties as we go along. Log base b of b to the x is x. So the example I have for you here is log base 10 of 10 cubed is equal to log base 10 of 1,000, which you've already seen is 3, since 10 to the third power is 3. So I put these little slashes here to indicate that if you're having trouble remembering this rule, think of these as canceling each other out. Okay, in other words, the log to base 10 of 10 cubed is going to be 3. That's what this is telling me. For example, the log to base 10, well, let's make it base 8, just for a change of pace, of 8 squared, or 64, is just 2. Okay, that's what the first one means. And if you're using natural logs, this implies that log of e to the x is x, because remember, the base of the natural log is e. Now, this one follows by the same logic. B to the log b of x is x. So let's look over here. This is saying that 10 raised to the log 10 of 1,000 power is 1,000. Okay, in other words, because log 10 of 1,000 is 3, 10 cubed is 1,000. So it's almost as if these were canceling each other out. So you just end up with 1,000. And that implies, in terms of natural logs, e to the log x power is just x. And you can think of e to the x and log x as being inverses of each other. Now, what's interesting, I'd like to show this to you on Symbolab. Symbolab is actually capable of putting more than one graph at a time on the same axes. So here's what we're going to do. We've already seen the function of log x. I chose different colors because it's easier to see them. This is the purple one on the bottom. You're very familiar with it. This is y equals log x. But this one, the green one, is y equals e to the x. If you look at them carefully, if you could imagine drawing a straight line through the origin, the two curves are symmetrical. They're mirror images of each other across that line. Okay, so you can see visually that they do appear to be inverses of each other. Okay. So, in other words, it's like I said, it's almost as if they cancel each other out. Log e to the x is x, e to the log x is x. We're going to get a lot of usage out of these properties, by the way, because often what we end up needing to do when there's logs and exponentials involved is we're trying to solve equations that are very complicated. And we should be able to use these rules to help us simplify our equations to make it easier to solve for them. Now, here's some algebraic properties for logs that will also come in very handy. So for example, no matter what the base is, the log of xy is the log of x plus the log of y. Now, of course, we're assuming that b is strictly positive. We don't use base b. Anything above that, though, this property will hold. Okay. By the way, why would that be? What good would, if you had base 0, anything raised to that to a power of 0 would just be 0. So instead, we focus our attention on the strictly positive bases. And so in other words, the log of a product equals the sum of the logs. So here's an example. The log of 1,000 could be rewritten, if there's a good reason for this, as a log of 10 plus the log of 100, because the product of 10 and 100 is 1,000. Now, you probably, if you already had log of 1,000, you probably wouldn't rewrite it like this. More likely, you would have a result on the right, which you would rewrite as the one on the left, because that would be considered simpler. And you know that often in math, we try to simplify our results. In fact, usually our goal is to keep the results as simple as possible. The one on the right is a bit messy, so we would probably want to convert it into the one on the left. So we can go either way. If we have a sum of logs, we can rewrite it as a product of a single log, or if there's a good reason for it, and we have a log of a product, we can rewrite it as the sum of those two individual logs. Now, here's another one where I've given you the results so we can prove it. Log base 10 of 100 is 2. I'll remind you that this is because 10 squared is equal to 100. But based on what we just saw, the so-called product rule, since 100 equals 10 times 10, that means that the log base 10 of 10 plus the log base 10 of 10 is the same thing. And in turn, that equals 1 plus 1, and it's also 2. It has to be. They are the same thing. All right. Now, this one is the same, except that there's 3 terms. It's a product of 3 terms, which means we can rewrite it as the sum of 3 terms. And once again, you may not want to take the first term. If this is your final result, you'd probably just leave it like that. But you never know. It might come in handy to split it up like this. More likely, you'll start here and work your way back to this more simple version. All right, now, if there's a product rule for logs, there clearly has to be a quotient rule. The quotient rule is just essentially an extension of the product rule. What it tells us is that if we have a log of a ratio instead of a sum, we now have a difference. Okay, so the log of a product is a sum. The log of a ratio or quotient is equal to a difference of logs. Like if you had log of 3x squared over 4, if you wanted to, you could rewrite it as the log of 3x squared minus the log of 4, and vice versa. Or with this case, and by the way, the reason why these arrows are here is to remind you that these all have to have the same base. Otherwise, this doesn't work. Okay, in other words, if you had something like this, this would not equal log 5 or 6 xy for any base. Because they're two different things. Okay, log 5, log 6. Here it's different because they're both the same log. They have the same base. Now, the third and final rule that we need for now is one that will be proved to be enormously helpful. The power rule, which says that the log of x to the n power equals n times the log of x. That's going to save us a lot of grief. If we use this properly, you can take some incredibly messy equations and simplify them with this wonderful rule. Okay. So for example, the log base 10 of x squared could be rewritten as 2 times the log base 10 of x. Now, I just want to demonstrate why this is happening. Log 10 of x squared could be written as log 10 of x times x, which now I can split up into a sum. And you can see I've got log 10 of x plus log 10 of x, which is 2 times log 10 of x. So in other words, the power rule is also a simple extension of the product rule. In fact, all three of these rules are really just different versions of the product rule when you come right down to it. But, it's nice to know that there's three. It's easy to remember them. But remember, they're all directly related to each other. So for example, yeah, here it is. It's the same thing. It's the proof of why this would have to be true. Log x squared is log bb, xx rather, and then we break it up into two terms, and then they're both the same. So we just write that as 2 log b. All right. Now, sometimes we also want to simplify in order to even use these properties. For example, we know that the square root of x is x to the 1/2 power. And so that means that in this case, log 10 of radical x could be rewritten as 1/2 of log 10 of x. And then similarly, log 10 of the cube root of x could be rewritten as 1/3 log 10 of x. Okay. So we should remember this key detail right here. Now, here's another interesting one. This one is going to be simplified a couple of times. So we got a product and a quotient. Okay. So we have log x to the 4th plus log y minus log 7. And then this term can be simplified even further with the power rule to 4 log x. Then we still have log y minus log 7. So again, if you had a result from some problem or other that looked like this, you might be tempted to rewrite it like this because it's just neater. But there may be times when breaking it up like this can help you because you're combining it with some other expression, and it might make things more straightforward. Now, here's a few more of these. Log base 10 of radical x, as you can see, well, we've already seen one just like that. This is this interesting one. When you see something like this, log cube root of x squared, that's actually x to the 2/3 power. I've explained it up here. Why is this happening? Because what this really means is that you're taking x squared and taking the entire expression and raising that to the 1/3 power. And you might remember the rule that if you have a to the m power all raised to the n power, you end up with a to the m times n. And that's what's happening here. X squared raised to the 1/3 power is the same as x to the 2/3 power. And we write that as the cube root of x squared. So that's why this is equal to this. And then this. Okay. So notice if you rewrite that as x to the 2/3, it's easier to see that using the power rule, we can simply rewrite this as 2/3 of log x. And again, this will come in very handy. Sooner or later, you'll see when we start doing some of these problems, it'll be very helpful to be able to do this. And here's a few more. 4 log x is log x to the 4th. 5 log 3 of 2 can be rewritten as log base 3 of 2 to the 5th, or log base 3 of 32. Now this one can be rewritten as log base 10 of 100 squared, which is 10,000. And that turns out to be 4 because 10 to the 4th is 10,000. Now, this is the formula that I promised you earlier. Remember, I mentioned that there can be logs for any base that we could imagine, as long as they're positive. And the calculators don't seem to have all the other logs on there. Why not? Because we don't really need them. So this is the formula right here. The log of any base of x can be rewritten as the log of some other base n of x over b. So just to make it clear, I've written an example up here. Imagine you had log base 2 of 10. And you find log base 2 to be awkward, or it's not on your calculator. How do I solve for this? I need the numerical value. So what I can do is rewrite this as the common log of 10 over the common log of 2. It doesn't matter what base I choose here, as long as it's the same for both of them. And then what I actually did was I went to my calculator and figured them out. So I've got 1, the first one, the one on top, the numerator is clearly 1. The log base 10 of 10 must be 1. The one on the bottom is about 0.301, and that ratio is about 3.32. Now, I wanted to point out, that's what this is doing down here, that the base is irrelevant. I could have just as easily rewritten this as natural log of 10 over natural log of 2. Okay. As long as the base is the same in both cases. Remember, the x goes in the numerator, the base goes in the denominator. Now I can look these up on my calculator, and you can see the numerator is different. It's 2.303 instead of 1. The denominator is 0.6931 instead of 0.301, but the ratio is the same. That's all that matters. So the log base 2 of 10 is about 3.32, and here's how we can figure it out with our calculators with this change of base formula. And that's why the calculators don't have to have every possible logarithm under the sun. Otherwise, you'd have to buy a whole calculator just for logs. Luckily, we have this formula, which makes that unnecessary. Now, I'm sure that Symbol app doesn't need to do any of this. Here we go. What did I say? Log base 2 of 10. Oh, I think it's confused. It doesn't understand that I want the correct value. Man, well, it's not really getting the point, is it? I don't know how to ask it for the actual numerical value. I really don't. Oh, there it is. It was hiding. Okay. Y is 3.32. Right, exactly. I'm telling you, this thing is so, let's just say it's not terribly user-friendly. I'm sure it's powerful as could be, but man, what a learning curve. And then here's another one. Log base 2 of 100, which we know is 2, could be rewritten as log 2 of 100 over log 2 of 10. Or natural log of 100 over natural log of 10. And what I did was I went to the calculator, I figured out what they were, and you can see that it's clearly just 2. Over here, we might have some slight rounding differences, but this is equal to 2. Now we're going to solve some equations. Now here's an interesting result. And this is due to the properties of logarithms, by the way. If we have an equation like this, b to the s power equals b to the t power, this can only be true if s equals t. So in other words, imagine we had something like this. To the x, 2 cubed. The only way this can be true is if x is 3. Okay, and it's really that simple. So you'll be able to use this property to take some fairly complicated looking equations and solve them without too much difficulty. For example, here, what if you had this staring you in the face on a test? You might say, oh my God, what do I do? But because of that one-to-one property for exponential equations, this implies that x minus 1 equals 2x minus 4. And once that's done, you can just rearrange it algebraically and solve for x. And that turns out to be 3. So this tells me that x equals 3. And you can see, I've done it up here. This is the double check. Just replace the x's with 3's. And you'll see that, yes, both sides are equal to each other, and they're both equal to 2 to the second power. All right. Now, here's another one, which at first glance does not appear to fit in here. It doesn't look like we're allowed to use the one-to-one property, and yet, look what I was able to do. 256, it turns out, is 4 to the 4th power. So look what I've got. 4 to the 4th equals 4 to the x minus 5. And that means that 4 equals x minus 5, or 9 equals x. Okay. Now let's look at a case where, again, it may not be clear that we're allowed to use the one-to-one property, and yet we are. Let's look at this next one. Suppose you ran into this one. 3 to the 4x minus 7th power equals 3 to the 2x over 3. I penciled in that 1 there because clearly that's equal to 1. Now, the key here is that based on the properties of exponents, when I have the same base here, this is equivalent to 3 to the 2x times 3 to the minus 1 power. As you can see over here, that means I'm going to add their exponents, and I end up with 3 to the 2x minus 1 power. So this line comes from that. Basically, I took this ratio on the right and reduced it to 3 to the 2x minus 1 power. And now all of a sudden I can use the one-to-one property. Therefore, 4x minus 7 equals 2x minus 1, and the rest is straightforward algebra. So in other words, the trick here was taking the messy expression on the right and rearranging it in such a way that I can find the right way that I can now use the one-to-one property. Otherwise, there's other things you could have done, but I think this is a pretty straightforward way of solving for this, what appears to be a very messy equation. You can see algebraically, this is just equal to 3. Now, what about logarithms? Is there an equivalent one-to-one property for logarithms? And the answer is yes. So let's say it was something like this. Now you look at it and say, you know what? I've got these two exponential functions, but sadly they have different bases. So I'm in trouble now. But are you in trouble? You are not. Why? Now remember, the so-called power rule of logs tells me that the log of any base, x to the n power, is n log x. So let's try this experiment. Can I take the log of both sides? Sure. I can perform any operations on both sides of an equation without changing the values. This implies that x, I'll tell you what, let's do natural log just to keep it simple. And only because I'm looking ahead, I see that's exactly what I did. It doesn't matter which log you pick, but just to be consistent with my examples, let's use natural log. This one implies that x plus 2 log 5 plus equal, oh, what did I do? This should have been an equal, sorry. X log 4. Now, it's still a mess, but we're getting closer to being able to solve for it algebraically. So skipping ahead, this is where we were. Up here, I've just reviewed some of the properties that we need. And now I can distribute the log 5 over x plus 2. So I've got x log 5 plus 2 log 5 equals x log 4. Now, the only term here that contains a variable is this x log 5. What I'd like to do is get all the constants. Oh, I'm sorry, there's two x's. We want them both on the left. We want the constant on the right. We want to keep them separate from each other. Yes, there's two x's here. We bring them together on the left. On the right, we have the only constant. And then we can factor out and then we can do some simplifications. Okay, so when you get the x's on the left, we have this and we have this on the right. I've done some factoring, and now this is what I was referring to. Log 5 minus log 4 is the same as log 5 over 4. This one I'm going to leave it like this, although I could rewrite it as log of 5 to the negative 2 if I want. And now I'm going to divide both sides by this expression because it's simply a constant. And so my final result is negative 2 log 5 over log 5 fourths. And then when you plug them into your calculator, you'll see that that ratio is approximately equal to negative 14.44. So the tricky part in the beginning was recognizing we can't use the one-to-one property of exponential functions because we have different bases, but we can still use logarithms. Now, by the way, I just want to point out, if you'd used a different base, 10, for example, you still would have gotten a final result of negative 14.44, because as we've already seen, the ratios of the logs would have been the same. Not the individual values, but the ratios. So the choice of base, when we do something like this, is irrelevant. We may find that some choices are more convenient than others, but the rule itself doesn't matter. So anyway, let's take a look at this example. And what we're going to do here is solve logs with logarithmic properties. Questions like, for example, this one, log 2 base 2 of 2 plus log base 2 of 3x minus 5 is 3. I'm going to combine these into a single product. The 3 is on the right-hand side. So I've actually got log 2 of 6x minus 10 equals 3. Now, that implies, based on the property of logarithms, that 2 cubed is 6x minus 10. Because remember, what this means is that I'm looking for the exponent, 3, so that when I raise 2 to that power, I end up with 6x minus 10. Then in turn implies that 8 equals 6x minus 10. Add 10 to both sides. 3 equals x. So the whole challenge here was not rearranging everything to get to this point. The challenge was recognizing that based on the definition of logarithms, this equation implies that 2 cubed is equal to 6x minus 10. Now, by the way, because you don't have a log on both sides of the equation or an exponential, that would be a hint that maybe it's time to instead use the just the basic properties of logarithms. So, like all calculus problems, I mean, the challenge is usually figuring out what technique you should be using. And that usually comes down to what information do you have, and is this making our life simpler or not by using this technique? Here's a pretty straightforward one. I mean, really. I don't even know why I threw this in here, but it's so easy. It's just straight ahead algebra. And there's really nothing else you can do about this. Except, oh, I know why it's here. We're not done. It may appear that we're done. We're trying to solve for x. This is an excuse to use the following properties. But let me just give you a hint where this is going. Am I allowed to do this? Yes, of course. And you'll remember that one of the properties we saw earlier is that e to the log x is equal to x, and log e to the x is equal to x. So here's two really powerful and useful properties you may want to memorize. And this is just because log and e to the x are inverses of each other. Now, e squared is a constant. It's approximately equal to 7.389. So in other words, if you need to know the exact value, now this is not incorrect, but if you need the exact value of x, you're not done. You need to rewrite this equation so that x equals some constant value, and now you've done that. You see? Well, then let's try this one. Now, by the way, whenever you've got something like this, you should always try to clean it up as much as possible. I want just the log on the left, and all the constants and other stuff should be on the right. That way, it's pretty clear that, again, e raised to the log 6x equals e to the 7/2, and e to the log of any f of x is f of x. Okay, in other words, this is just a special case of this. This applies for any function of x. So I've got 6x equals e to the 7/2, which is, of course, a constant, and this is my final result. And that's some value. We can look it up on our calculator if we really need to. Oops. So finally, we're building up to this final result. The one-to-one property for logarithmic equations tells us that if we have the same base Log B of S, log B of T implies that S equals T. Okay, so remember what we had before with exponentials. Was this. It's the same thing. They're just rearrangements of each other. They're not two separate conditions. How do you know that? Because all I would have to do is take the log base B of both sides of this equation here, and I'd end up with this one. Okay, but it's easy to remember this as the one-to-one property for exponential functions and the one-to-one property for logarithmic functions. You can think about the logic going on behind the scenes as well, but to actually use this stuff, it's nice to have these memorized or at least understand how they work. So let's look at a case of this. We start out with a pretty messy expression. We consolidate these using the quotient rule. Into log 2 of 3x minus 2 over 2 equals log 2x plus 4. But now based on our one-to-one property, that reduces to 3x minus 2 over 2 equals x plus 4. And now the rest is just simple algebra. Okay, so let me just leave it there for a second. So you can see what has happened here. Yeah, that's all you had to do. And then this is the easy part, just straight ahead algebra, and you end up with an answer of 10. All right, so that was pretty intensive, I must say. So what's coming up next? This is the end of 1B. So we still have 1C to get through. 1C is our intensive review of trig functions. We don't want to dwell on it for too long. We're not trying to, derive all the results, let's say, although I'm going to show you some of the derivations. We just need to review the terminology and some of the formulas because we're going to need these functions throughout the rest of the course. And I'm sure it's been a while since you used them. So we'll get quickly through that, and then we can get going on the new material, which is limits. Okay, we're going to see the concept of limits, which is used to derive an awful lot of results in calculus. And so it's an important concept. So that is what is coming up next. Now, by the way, don't forget, I've posted the first assignment on Moodle, and when you look at it, what I've done is it's just a list of problems from the textbook, which I would remind you is freely downloadable from the internet. The instructions are in the syllabus, and just go find those pages and look at those problems, and just do them. I've decided that the easiest way to do it is just to have you write them out on a piece of paper as if you were in school. And one thing you might want to, I'm not getting any commissions for this, but I found a product, a technology related product that actually works well, to my great surprise. And it's called Adobe Scan. Let me show you the app on the phone. I don't know if you can, you have to, of course, download it. It doesn't come with the phone. There it is. And now the lettering is backwards, of course. Adobe Scan. And basically what it does is say, listen, what do you want to take a scan of? You hold it over the document, you punch a button, and it takes a really good quality picture of whatever it is you're doing. Much better than if you take the camera and take that same picture yourself. Now, this has been my experience. You can take pictures of your homework, but they don't always turn out so well. There can be issues with the lighting and all this and that. I think you're better off using this because it's free and the quality is very, very good. The only thing you have to do is go through and see how to email it back to me. It's in there somewhere. It's not that complicated, but make sure it knows you want to take that document you just created and email it back to me, and you'll be all set. Now, if you own a printer, you don't have to worry about any of this because you can scan it into a PDF document. In the past, I've noticed a lot of people don't seem to have access to that. I don't understand how that's possible. But most of the classes that I've had, very few people said, yeah, I've got a printer. I can take care of this with no problem. Well, all right, that's okay. Might as you can just use this. So I find that Adobe's products are all top quality. I rarely have any issues with them. And they make products like Photoshop and things like that, and PDF. They make that, so they know what they're doing. So I'm not surprised that the scan works so well. Very rarely do I run across technology that works well, but this is one of those cases. So anyway, so like I said, next time we'll be talking about trig functions. We don't want to spend too much time with that, but we'll just make sure that everyone remembers the basics, and then we'll carry on from there. So I'll see you all next time.